Hello dear students, hope you are all fine. This is session number 1 of chapter 11, carboxylic acids and derivatives. By the end of this session, you should be able to define monocarboxylic acids, deduce their general molecular formula, name them, identify their isomerism, and list some of their physical properties. Carboxylic acids are organic compounds that have the functional group COOH. This functional group is called carboxylic group. In this chapter, we are interested in saturated open chain monocarboxylic acids. Saturated means that they have no double bonds between carbon atoms. Open chain means that the carbon chain is not cyclic. And monocarboxylic acids because they have only one carboxylic group in their carbon chain. Carboxylic acids are found in our everyday life. You can find them mainly as ethanoic acid in vinegar. They are also found in butter, in apples and apple juice, and in lemon. Now it's your turn. Try to define the carboxylic acids. Carboxylic acids are organic compounds that have the carboxylic group in their chain. The carboxylic group can be written like that or like that. Let us try to write the condensed structural formula and molecular formulas of the first three carboxylic acids. The first carboxylic acid contains only one carbon atom, so its molecular formula will be HCOOH. Okay, HCOOH, and thus its molecular formula is CH2O2. Let us together write it in this way for the purpose of finding the general molecular formula. The second carboxylic acid is CH3COOH. Its molecular formula, give it to me please, C2H4O2, and of course you can write it in this way by yourself. It is C2H2N2O2. The third carboxylic acid is this. It can be written as a molecular formula and in this way. Can you predict the general molecular formula starting from this writing of the molecular formula? Yes, of course. You can notice that the number of hydrogen atoms each time is double that of carbon atoms, and therefore the general molecular formula of saturated non-cyclic carboxylic acids is CnH2nO2, where N is the number of carbon atoms. It also can be written like RCOOH, where R can be a hydrogen atom. Let us together try to name carboxylic acids. Naming carboxylic acids start from alkane, the name of an alkane, but by replacing E with oic, and then we add acid. Start with the first example. This is a carboxylic acid that have only one carbon atom. Its name is derived from methane, but by adding oic acid, methanoic acid. Let us together try to name this. It will be ethanoic acid, and this is propanoic acid. This contains 4 carbon atoms, so its name is derived from butane. It will be butanoic acid. Let us consider this exception which you have to know. This is benzoic acid. Benzoic acid has the molecular formula C6H5COOH. It is not open chain and not saturated carboxylic acid, but you have to know it. Now let us together try to name branched chain carboxylic acids. This is an example. First step, to name this carboxylic acid, what will you do? Of course, you are going to choose the main chain. The main chain will be the longest chain containing the functional group. This is the main chain, and then you have to number this main chain. So, from where will you start numbering? Will you start numbering from this side or from this side? Of course, from the functional carbon. This is carbon number 1, 2, 3, and 4. And you will see that methyl is on carbon number 2. So together let us put the name. The name is 2-methyl we have 4 carbon atoms, so butanoic acid. The name is 2-methyl-butanoic acid. Listen please. In carboxylic acids, you do not have to mention the position of the functional group because it is always on carbon number 1, like aldehydes exactly. Now, title number 3, isomerism. Consider a carboxylic acid of molecular formula C5H10O2. Write all the possible content structural formulas of this carboxylic acid. So you have to draw all the possible isomers of this carboxylic acid. First isomer that you have to draw is which one? I think all will you choose the easiest one, and you are right. The easiest one is to put 5 carbon atoms beside each other with 1 carboxyl group at the end. Okay, so the unbranched isomer is the first isomer to be drawn. This is the first isomer 1, 2, 3, 4, and 5. 5 carbon atoms with the carboxyl group at carbon number 1. The second isomer will be which one? I think you will choose to draw 4 carbon atoms beside each other and take 1 CH3 as a branch to this carbon at first and to the third carbon at second. So this is isomer number 2 and this is isomer number 3 when you move this branch to carbon number 3. The fourth isomer is this, where you put 3 carbon atoms in the main chain and 2 branches on carbon number 2. Remember, each time you add a branch to drop 1 hydrogen. So here we had CH2, but when we put a branch, we drop 1 hydrogen. Remember this, okay? Now you have to give the systematic name of each isomer. This isomer, let us give its systematic name. 1, 2, 3, 4, and 5. From pentane, we put pentanoic acid. This, it's easy for you, isn't it? Start numbering from the carboxyl group. It has the most priority. We start from here. 1, 2, 3, and 4. 2-methyl butanoic acid. 4 carbon atoms, so butanoic acid. Here, 1, 2, 3. 3-methyl butanoic acid, and here we have on carbon number 2 2-methyl groups, so 2,2-dimethyl propanoic acid. Now consider the structures below having same molecular formula C4H8O2. All have the same molecular formula but different structural formula, so they are what? They are isomers. Specify the type of isomerism that exists between structures A and B. Listen please. A and B. Look at them. They have same molecular formula C4H8O2. They have same position of the functional group, but they have different arrangement of carbon atoms, different skeletons. So they are called what? They are called skeletal isomers. A and C. What is the type of isomerism between A and C? Take a look, please. They have same number of carbon atoms, but what? Different functional groups. This is a carboxyl group. This is an ester group. Different functional groups. We say they are what? Functional isomers. Okay. Can we have positional isomers? Note that there is no positional isomers for carboxylic acids. Can you figure out why? You know, of course, because the carboxyl group is always on carbon number 1, so they will have no positional isomers. Title number 4, Physical Properties of Carboxylic Acids. Let us together have a look at table 11.1 on page 252 in your national textbook. You are given the boiling points and the solubilities of some carboxylic acids which are straight chain. Question number 1. Referring to the boiling points given, above. How does the boiling point vary with the increase in the number of carbon atoms? Notice here, as the number of carbon atom, or as the length of the carboxylic acid, or as the molecular weight of the carboxylic acid increases, how does the boiling point changes? Do you notice that it increases with the increase in the number of carbon atom of straight chain carboxylic acid? Yes, it is. So boiling point increases as the molecular weight of the carboxylic acid increases, or we can say the boiling point increases as the number of carbon atoms in straight chain carboxylic acid increases. Question number 2, how does the solubility vary with the increase in the number of carbon atoms? How can you say it? How does it vary? Of course, you notice that the solubility is infinity for the first 4 carboxylic acids, and then it decreases. So solubility decreases as the number of carbon atoms, or as the length of the carboxylic acid increases. Now let us study the effect of branching on boiling points. You are given 3 organic compounds, all having same molecular formula C5H10O2, and all having same functional group. How does the boiling point changes as branching increases? Do you notice that the boiling point decreases as the branching increases? So branching decreases boiling point. Let us summarize the physical properties. All carboxylic acids are liquids or solids at room temperature. Boiling point increases as the molecular weight increases. The first 4 carboxylic acids are highly soluble in water. As the carbon chain increases, solubility decreases. Now, why is the boiling point of carboxylic acids relatively high compared to the previous organic compounds? In fact, if you take a magnified look to a pure carboxylic acid, let's take for example ethanoic acid. A magnified look showed that carboxylic acids form special structures called dimers. These dimers are stable forms and stable structures. They are stabilized by the formation of hydrogen bonds between fairly positive hydrogen atom and fairly negative oxygen atom of the other molecule. This hydrogen bond needs more energy to be broken, because they are 2, they need more energy to be broken than other organic compounds, and thus they have high boiling point. Application: match each of the following boiling points to the corresponding organic compound. You are given 3 boiling points, 21 the least one, 101 is the highest, and 78.5. You have 3 organic compounds, ethanol, and ethanoic acids, all having same number of carbon atoms but different functional group. Which of these will have the highest boiling point? Of course, the carboxylic acid, isn't it? Ethanoic acid will have the highest boiling point, which is 101. And which one will have the least boiling point? Of course, the aldehyde, which cannot make hydrogen bonding, so it has the least boiling point. It will be 21 degree. This is for the aldehyde ethanol. This is a boiling point of ethanol, and of course this is for the ethanoic acid. Application number 2, arrange the following carboxylic acids in increasing order of boiling points: ethanoic acid, propanoic acid, and butanoic acid. They are all carboxylic acids having different number of carbon atoms. Do you still remember the rule? As number of carbon atoms increases, the boiling point increases. So of course butanoic acid will have the most boiling point, then propanoic acid, and the least boiling point of ethanoic acid. Application number 3, give the name of the following organic compound. So you have to give the IUPAC name of this compound. First of all, you have to find the main chain. Where is the main chain? 1, 2, 3, 4, and 5. Is this the main chain or is this the main chain? 1, 2, 3 with this group together, the main chain. Which one is the main chain? I guess that most of you will say that this is the main chain. But this is not true at all, because C6H5 is a cyclic group. It must not be the main chain. All the time the main chain must be linear chain. This compound, all of it together, can be represented in this way. So C6H5 is this group, C6H5. It's phenyl group. It's derived from benzene. So benzene, when it becomes a branch, it becomes C6H5. This is C6H5. Its name becomes phenyl group because it becomes a branch, and it is not a main chain. The linear chain is a main chain. Locate it and start numbering. From where will you start numbering this time? Of course, the priority is all the time for the functional group. So 1, 2, 3, 4, and 5. 3. Phenyl pentanoic acid, because we have 5 carbon atoms, pentanoic acid. Don't forget, this is phenyl group. This is the end of session number 1 of chapter 11. Thanks for your attention. General summary for what we have taken. We have taken how to point and name the functional group of carboxylic acids, how to name them, how to give their isomers, and to interpret their physical properties. The main reference is your national textbook. It's your book. And thanks for all the contributors.